The Chancellor, His Excellency Dr. Thabo Mbeki, the Vice Chancellor and Principal of UNISA, Professor Puleng Linkabula, both of whom are sending greetings and congratulations. They're watching this lecture. To the professor that we're inaugurating this evening, Professor Makwena Justice Moloto, his family, friends and loved ones. Members of the College of Science, Engineering and Technology, and the staff, Executive Dean in particular, who's participating in this program, admin, students across the board, supporters, funders, UNISA alumni, distinguished guests, boys and girls, and Prof. Moloto again, the person that we're installing this evening, Sanbunan Molwin, Tobelang Dumelang of one. Good evening, Jambo. I acknowledge all protocol. My name is Professor Tenjwe Meiwa. I'm the Vice Principal responsible for the College of Science, Engineering and Technology, and by extension, Professor Moloto's lecture. Ladies and gentlemen, colleagues, greetings and welcome to this lecture, the inaugural lecture, wherein we are installing Professor of Nanostructured Materials at the CSET, and he's affiliated with the institute that we know as the Institute of Nanotechnology and Water Sustainability at the Science Campus. Please allow me to acknowledge the respondent, and we thank Professor Reva Prazado of the Department of Chemistry at the Faculty of Science and Agriculture at the University of Zululand for agreeing to serve as a respondent. We thank you, Prof, for heeding our call. These are times that as a university we pride ourselves so much in, because we are having our professorial ranks that are swelling. And the swelling of those ranks is due to the contribution that's being made by the likes of Prof. Moloto. And hence we take such events of installing the professorate very, very seriously, because through these events we demonstrate and are indicating the fact that our researchers, our academics have indeed done the work that's expected of them. It's a cadre of professors and that Prof. Moloto is part of that is adding expertise and would have indeed been doing a lot of work over the years leading to this level of a full professor. Somebody who oversees research projects, who leads those projects, who publishes quite eminently, as is the case with Prof. Moloto, who's a mentor of students at higher degrees, who produces and reproduces research. I invite you, ladies and gentlemen, boys and girls, to use the comments chat box to congratulate Prof. Moloto, but not only congratulate him, but including the congratulatory remarks, to give him ideas on how he could further his research, and that you could continue to participate through these comments, through his scholarship. Prof. Moloto will be introduced in more detail by the Executive Dean, Professor Mamba, who is participating actively in this program. I will not be coming between them, and after him we will have Prof. Moloto presenting his lecture. After Prof. Moloto, we'll have Prof. Reva Brasadu, who shall be responding to the lecture entitled Realities of Fabricating Nanomaterials, Past, Present, and Future Prospects. It's really whetting our appetite. Without further announcements, I will not be coming in, as I said earlier, but I now at this juncture invite Prof. Mamba to come to the podium. Prof. Mamba, please.
Acting Vice Chancellor, Professor Tenjwe Meiwa, who is also the Vice Principal for Research, Innovation, Commercialization and Postgraduate Studies at UNISA, who is presiding over this inaugural lecture. And of course, members of CSET, the College of Science, Engineering and Technology, that is the executive, all staff members, non-academic and academic staff who are here. And I'd also like to acknowledge the presence of the respondent, Professor Reva Prasadu, who is a senior professor in the Department of Chemistry at the University of Zululand. And I would like to acknowledge the collaborators, co-researchers, friends and relatives of Professor Justice Mokoena Moloto, who will be giving the inaugural lecture today. And I'd also like to acknowledge the presence of members of other colleges who are following this inaugural lecture. And ladies and gentlemen, I welcome you to this inaugural lecture of Professor Justice Mokoena Moloto. Before I invite him to come and give the lecture, I would like to read a biography of Justice Moloto. Justice Mokoena Moloto was born and grew up in the rural-based area of Kaseleka in Limpopo as a regular head boy who enjoyed school. He attended a local primary school and traveled daily to attend high school in the neighboring village. He subsequently enrolled at the University of the North, which is now known as the University of Limpopo, after completing his matric in 1991. After the financial and academic struggles, he completed his BSc degree where he majored in chemistry and zoology, and in 1996 and completed his honors degree in 1997 at the University of Limpopo. He then immediately enrolled for an MSc degree at the University of Western Cape, which he completed in 2000. With no academic break, he continued with his PhD at the University of Zululand on a part-time basis, since he was employed for 6 months after enrollment. His PhD was completed in 2005, and this was part of the NRF and the RSC, Royal Society of Chemistry, collaboration with the University of Zululand and the University of Manchester in an exchange program. Then he began his academic journey, where he obtained his PhD at the University of Zululand. And he spent 6 years there, followed by 2 years at Wits University, and later at the University of Johannesburg, where he was a senior lecturer at Wits and at UJ. 10 years later, he then surfaced at VUT, where he was appointed as an associate professor, and he spent 10 years at the Valley University of Technology. And now he is with us at UNISA, where he is employed as a full professor at the Institute of Nanotechnology and Water Sustainability, known as iNanos, in the College of Science, Engineering and Technology, located at the Florida Science Campus. Professor Moloto has more than 15 years of experience in conducting research, and he has published at least 100 articles, and these articles were peer-reviewed journals. And he also served as a reviewer in a number of committees which have been instituted by the NRF, amongst others, and he has been a reviewer of many scientific journals in the areas of nanotechnology, nanoscience, and material science. And he has served as a chairperson of the organization which is known as Nano Africa, where he hosted the conference at VUT, and he was the chair of that particular conference. He has presented his research work in more than 12 countries globally, and he serves in leadership roles, including having served as a chair of a department for a period of 2 years, and has been a chairperson of various research and innovation committees in the faculty where he was serving at VUT, and the NRF has used his services to be the chairperson of various panels. In terms of engaged scholarship, he has initiated a number of community engagement projects, particularly at the University of Zululand and at VUT, where these committees have served a various number of science-based school learners and educators in the neighboring places or villages or the neighborhoods of those universities which I've already mentioned. And because he's got a passion for educating students, he has assisted individual students so that they can get entry into university in terms of placement and also in terms of in-service training opportunities so that they could complete their degrees and their diplomas. Professor Moloto is a researcher of note, and he mentors students. And currently he's mentoring at least 25 postgraduate students and 2 to 4 researchers and some postdoctoral fellows. Some of the students are those whom he has led at his previous university and those who are currently enrolled with him at the University of South Africa. To date, he has supervised to completion no less than 28 postgraduate students at all the universities where he has been: University of Zululand, Wits, UJ, VUT, and I must stress that all these universities he has produced a doctoral student, except at the University of Zululand. There are 3 masters and 1 doctoral students who are completing or have completed their dissertations, and they are due to graduate in 2023. His research focus area is on the design, functionalities of semiconductors, metal nanoparticles, their synthetic aspects and interactions with other materials such as polymers in fibers and in composite forms for biomedical and water treatment applications. He's currently supervising and co-supervising 5 PhD students and 7 MSc students at UNISA and VUT. And also, we want to acknowledge his family and Professor Nosipo Moloto, who is also a co-researcher with Professor Justice Moloto, and of course the family which is here, who are here to support him, and because he wouldn't be where he is if it were not for the family who stood right next to him and supported him. So without any further ado, ladies and gentlemen, let me invite Professor Justice Moloto to give his inaugural lecture. Thank you.
Good day, everyone. As being introduced by Professor Mamba, the Executive Dean of College of Science and Engineering and Technology. My name once again is Professor Makwena Justice Moloto, and a professor in nanostructured materials at INANOS. And I would like to first thank Professor Lynn Kabula for the kind invitation for giving this opportunity for the inaugural lecture, and also to the Deputy Principal, who is Professor Meiwa, and also just to like to thank Professor Mamba and also the colleagues at the college for the opportunity. And also good evening, good afternoon for those who are watching as well. So now, when I was asked to give this particular request for giving a lecture, I thought of a couple of things, and one of those is really to look at the journey that I took for me to be where I am right now as a full professor today, being inaugurated. So hence the topic, looking into realities of fabricating nanomaterials, and also looking at what has happened in the past and currently, and also the future prospects, just to guide some of the youngsters that perhaps they will be watching and also want to be able to guide us through my journey. So this will be sort of the outline, starting from the current trends and future prospects, all the way down to acknowledgements. I think all the other items that are displayed, for those who are doing chemistry, they'll realize them on the periodic table that is displayed there. So now just to go deep into it, some of the current trends that you observe in our area of nanomaterials, or maybe let's say nanomaterials fabrication, there's a lot more focus on silver, titanium dioxide, and iron oxide, and primarily for these reasons that silver is being used a lot in biomedical applications, and titanium oxide the same, but you also find it in other areas that is being applied. So they find a lot of uses in the various ways that you can ever imagine be reported, in many different articles in the world. And iron oxide is also very much useful because it's got magnetic properties, and those magnetic properties we're talking about there, it's about the fact that they are very useful in the sense that you can be able to make materials out of them, and at the same time be able to recover them or use that particular property of magnetism to be able to recover them. And all of those, they can be incorporated into the polymer fibers. Hence, you can see that there's an aspect of nanofibers there, which is very much important to be able to relate to. That if you incorporate them into the nanofibers, then you spread even, the applications beyond just what they used to on their own. And I'll touch on some of those aspects as we go along. So now, my journey started when I was at the University of Zululand, and this was through the collaboration with the University of Manchester. And we started looking at exploring what complexes, or making complexes first. And out of those complexes, as much as they look great to be made in this way, like what they've learned from me for my master's, especially maybe just paying gratitude to Professor Dagwa there, who taught me about making complexes, we take those nice structures there and thermalize them and decompose them to make some metal sulfides, nanoparticles. Here's an example of cadmium sulfide, but you can make a lot of range of those that are shown on the sides here. And at the same time, you've got different type of ligands that can be used as far wide as possible, but the main source being either the sulfur or perhaps the oxygen or the selenide or the telluride, sometimes being to some extent the phosphide that you have done some work on. This is what you call single source precursor approach, where you have got one particular complex that you've made, and it's very clear that there's a metal sulfide bond, and that metal sulfide bond is important for you to end up with this cadmium sulfide material there. And these are some of the examples from the earlier stage in 1998 from Paul O'Brien's work, and we expanded that and explored a couple of different options, ranging from single nuclear complexes to multinuclear ones, and also sometimes varying the different ligands that you might think about being similar, like the methyl, ethyl, and comparative thiourea on its own, just to be able to understand what happens if you vary those particular functional groups on the ligands there. And of course, you get variety of products that comes out of there with the different properties that are dependent on the size and the shape. And one of the interesting things that also we observed is about the formation of the voids when you're making what you call the core shell nanomaterials from the same kind of complexes that you're making here. And when you do that, you end up with some voids forming, but this voids looks like some cavity that you can see on the onion-like structure here that often shows some layers of materials that can be derived nicely or can be related nicely to the formation of layers of a core shell structure. So now, all of these are really a drive to be able to demonstrate that your nanoparticles, they are so much shape dependent and also size dependent, such that if you are able to explore different properties that you've looked at in the previous slides about varying different functional groups and so forth, you can be able to control either the size or the shape of the nanomaterials, whether in terms of the shape, whether they are 0-dimensional or 1-dimensional or even 2-dimensional. And therefore, that is also demonstrated by, or is perhaps supported by, the way they grow and they formulate as the particles they're growing in the nucleation and the growth stage that we normally follow in making those nanoparticles. But the main important thing is that as they variation grows with the nanoparticles. They are such that you can still have one nanomaterial, one type of nanomaterial like cadmium sulfide, and play around with its properties such that from this particular bulk band gap of 515, you don't need to change to a manganese sulfide or lead sulfide to get a lower values there. You can still be able to take the same cadmium sulfide and play around with the size, and therefore you're engineering this particular band gap here that becomes discrete and therefore end up with different values that you can be able to lower that. And if you lower that, also the energy becomes higher. So it's essentially just engineering the band gap that results in quantum confinement of these materials. And this is just an example to show that in both solid state and solid solution state, you can be able to see also just directly by observation of color, that intensity of the color of same material can demonstrate the change in the shapes, the change in the size of the materials there. And these are the different conditions that can be able to play around with. I'll demonstrate some of those, some examples. And one of the other things that we try to do with this single source precursor was to say, if we can be able to make ligands, what if we can be able to make those ligands? In the process of making the ligand, you don't necessarily have to extract the ligand and perhaps change it to be, or extract it to be such that you can be able to see what bonds are forming in it, but just in situ, add your salt so that you can be able to end up with the same product rather than having a complex forming there. So you just go in the reverse of single source precursor route in a way. And you manage to get that and vary it, even the cake molecules that gave rise to, although there's some bit of agglomeration, but essentially varying the conditions even improves those nanoparticles even further. So now, having described all of those single source precursor route or approach, it has got its own shortcomings. One of them is the fact that people always talk about toxicity. And toxicity is still minimized in a way. When you introduce some capping environment around them, you still are able to control toxicity or minimize it to some extent. And also it brings, you introduce some organic moieties that are as a result of decomposition thereof. That makes additional aspect of safety to be worried about. So all of those they add towards toxicity. But also there's an element of temperature that is also very much useful, that when you make these nanoparticles in the same way that you did for single source precursor route, you often will work at higher temperatures. And therefore, it will be ideal for applications to come down to as low a temperature as possible. We'll see some examples as we go along as to how we try to mitigate against that. And therefore, we try to go the road of making water-soluble nanoparticles, especially for biomedical applications. These are a list of, a range of biocompatible molecules that you can find that can be very much useful depending on where you're going to target the use in the body of a human being or perhaps of any animal. And you can see that one of the perhaps, although this was successful, but also comes with its own challenge. And one of those challenges is the fact that once you do what you call this ligand exchange, where you're now swapping between the ligand that you started with that is not soluble to the soluble ones, you end up with particles that are not as big as they originally were, or perhaps even agglomerated like in this case here. But here you also can end up with some very nice discrete particles that are very small, and finally you can be able to see that they are become even smaller and smaller. The dissipation becomes improved. So these are the two approaches for water solubility, where you can be able to do ligand exchange, swap the two from water soluble to soluble ones like the sugars, or you can just directly prepare this in alcoholic medium and be able to generate the same nanoparticles thereof. And this is another example where we've used the same approach, and just to demonstrate that if you're preparing this in a normal HDA-based environment, which is your hexagonal amine-based environment, which is normally used a lot in the single source approach, you can sometimes be able to see the moment you start replacing the HDA with your sucrose or glucuronic acid, particles also remains with the same shape, except that to some extent sucrose is not as robust in capping or stabilizing the nanoparticles, such that particles they break a little bit and then the shape thereof becomes affected. So we also looked at the core shells that I described earlier, and in this particular case here we tried to see if we're adding zinc oxide into cadmium selenide and also taking cadmium selenide, adding into lead selenide, what really happens there. And we found out that when you vary the amount of zinc oxide that is added into the cadmium selenide solution thereof, at about 5 mils and 10 mils, that's when you end up with your spherical nanoparticles that are rather darker on the inside, showing that indeed on the surface and the inside are not the same, which are characteristics of core shell structures. But as you increase the amount of zinc oxide, you end up with high amount of zinc oxide particles that you can see here from a structure that shows very crystal-like structures which are typical of zinc oxide. But on the contrary, when you're adding if you're adding cadmium selenide into lead sulfide, the contrary happens, such that at a lower time, you still get very nice, small nicely sized distribution of particles. But as you increase the time, you start realizing that lead sulfide start growing to be bigger and makes some kind of a rod-like structure that becomes with an assembly of CDSE on the surface thereof. And also the optical properties, they also tell the same story, that indeed you've got a lot more CDSE dominating on both sides because of the fact that you've got cadmium selenide forming on the surface there. We also looked at the silver-based nanomaterials and also the plant extracts. I will take you through some examples just to show some of the things that we've been able to do and demonstrate. And one of those is that when you look at silver selenide, especially looking at varying Kp molecules, we tried to see if we are able to bind glucose, ascorbic acid, and chitosan, and compare that perhaps with green tea, because green tea is obviously related to plant extracts. What are the kind of variables that controls or perhaps can be able to play a role in growth of these nanoparticles? And you realize that glucose is still much better than ascorbic acid and chitosan. And the green tea also shows some, these are very big particles which are not spherical, which are non-spherical. But you can be able to see that now, at least with green tea, there's some variable that comes to play a role there. And you try to say, okay, maybe we can just explore this starch a lot more, such that if you do follow the extraction time, and also at the same time, just to vary the amount of silver that you'll be able to add into it, how much effective will the particles be able to form? You can see that especially for these two here and these three here, that particles are still very nicely loose, and therefore it means starch is still giving such kind of improved, less agglomerated particles and more dispersed ones. And also at the same time, we thought if we are able to bring in this element of biomedical applications, why not we try and start doing some applications, and we explored and some antibacterial activity where we realized that indeed they're showing very good signs of antibacterial activities there. And we continued with the silver sulfide from silver selenide, but this time using thiourea as a source of sulfur, but varying the starch and silver ratio, where you can see that varying the silver ratio, where you're doubling the amount, the more you double, the more you increase the amount of your silver source. Actually, the lesser you have got the amount of silver source, the smaller the particles became, as compared to when you've got the 1:1 ratio. And at the same time, when you took the 1:1 ratio, and we tried to now vary the percentage of starch that you added into it, you can also see that trend where particles are also becoming smaller as you increase the amount of starch that is added in here. So now, when you look at gender-related plant extracts, because green tea was obviously demonstrating some different features to what you normally see from spherical, even though these ones are agglomerated, we thought perhaps we could explore them further. And we found out actually when you use this particular plant here, Combrata mole and Eucomis autumnalis, and try to see if, for instance, in this case here, we try to see how much of the organic molecules, organic moieties are there, only to find that they're predominantly having flavonoids, which are in a way, controlling the particles the way they will be. as compared to starch and other chemical molecules that I've done before. You can see that the control is not better, but as you increase the amount of the flavonoids, the amount of extracts, the particles become even much more smaller, which is an opposite trend that you normally will observe in other scenarios there. And the same happens when you increase the time, where you can see that the particles also become smaller and smaller as you allow them to interact with the plant extracts in that scenario. We also tried in terms of water solubility to say, what if we tried amino acids as well, just like we tried the glucose, ascorbic acids and the plant extracts, to say amino acids, they've got very good properties that you can find a lot common in the human body as well. So, but now if you have to interact them with these metal sulfides, and here are some examples of those that I've tried to show you in this case. You've got copper selenite, copper sulfide, and zinc sulfide. And you can see down here that when you're using L-cysteine, particles are not as controlled as maybe when you're using HDA as an example, but there's still some change in the way they form, primarily driven by the fact that you've got different functional groups. You've got carboxylic acid group, the amine groups, and therefore that doesn't orientate particles in one direction. Therefore, you end up with rather non-spherical particles. The same applies here for your aspartic acid that is being used there. And in addition there, you realize that the MIC values are also showing some signs that says, for copper sulfide in particular, there's a greater deal of MIC value being lower as compared to the rest, where the activity against the bacteria is starting to emerge greatly. And we explored that even more and say, what if now we're able to introduce combining the two amino acids to make peptide bond formation in them? And at first, it was about the fact that we used also titanium disulfide, and against these particular chemical molecules, the amino acids. But when you combine them, you find that actually, in most of the time, you find a lot of interactions such that instead of them having the opposite effect, they end up accelerating the multiplication or the growth of bacteria. It's not necessarily a bad thing, still a positive thing to be able to look at and explore further to say, what is really happening here? Because is it about the titanium sulfide, or maybe is it about the peptide bond that is forming that is encouraging the growth of cell walls in the bacteria, or that is encouraging the growth of cell walls in the bacteria? Therefore, it does the opposite of what we intended to do. And also we looked at polymer fibers, where you use electrospinning technique. This is the setup that I've used at VUT. I think it goes up to about 90 kilovolts, but we've never really gone that as much high as that value. We always used as low voltage as possible. And these are some of the polymers that we've really explored, and I'll take you through some examples in that particular case there. And the first one that we tried at some point at CSIR was trying to see if we are able to take cadmium selenide and prepare it and incorporate into these two polymers here. And obviously this is what it looks like, non-spherical particles of CDSE. And you can be able to see that the moment you start introducing it to your polymers, they start influencing the polymer's diameter, as well as at the end of the day, when you increase it more up to the highest amount, you start seeing the PPMA starting to coil, and therefore it forms like helical structure as compared to when there's lesser of it. So it demonstrates that indeed there's some influence of CDSE into the structure of the fiber diameters, or the fiber formation, the diameters thereof. And we also observed for PEO, whereas you add the amount of CDSE into PEO, the surface structure of your PEO is becoming different to when you've got PMMA, and therefore it breaks apart, as you can see from the images there, that they start to break even more as you increase the amount of CDSE. But also at the same time, when you look at the thermal stability, you can tell that PEO is not as stable as perhaps PMA will be like. And this also demonstrates when you're adding your copper selenide into the same PMA, which shows some variable change in the thermal stability thereof. The other thing that we tried to explore was to say, since you're adding this copper selenide and these nanomaterials into the polymer fibers, what is happening in terms of their conductivity? And as you add in the amount of your nanoparticles into the polymers, you're also introducing some conductivity, and therefore at a very small amount of copper selenide being added, we realize that that's where you've got the highest conductivity as opposed to what you normally expect. This has not been explored even further, but it's a very strange phenomenon that you will expect maybe to increase the amount of copper selenide to have increase in amount of conductivity, but at the same time, this increased conductivity at 0.6 copper selenide is what informed the fiber diameters to be even smaller compared to the rest of the increase that is being observed there. Silver selenide was also being incorporated into the polymers, but first, before you do that, we prepared it by using different capping molecules. HDA is being reported, as we've talked about that earlier, and also what you call trioctyl phosphine oxide. And where you can be able to see that indeed for HDA, you've got better control of particles and better formation of particles compared to what you have for topo. And therefore, we continued with the HDA capped nanoparticles and incorporated them, even though we know that HDA is not soluble and it's not maybe biologically friendly, but we just wanted to observe in terms of its stabilized nanoparticles, whether they can be able to disperse nicely into the fibers thereof. And as you can see that the more you add nanoparticles, as you increase the amount of nanoparticles into the fibers, there's a decrease in the diameter. It reaches a particular point where now there's no more decrease, but a critical limit where now there's no more decrease, but there's almost half the size of what you expect from the beginning when you don't have any nanoparticles there. This is in contrast to when you increase the amount of the polymer itself. If you increase the percentage of the polymer, you realize that the diameters also increase in that way. And this has been observed for many other polymer fibers, but we also looked at the chitosan PVA blend. Instead of just working with the one polymer, just blending the two polymers with different ratios here, where you can be able to see that indeed also these are affecting the blend itself, they're affecting the formation of the fibers, such that the more, because chitosan has got the problem of solubility, and also, even though it's highly biocompatible, but it's also got problem with solubility and charging as well. And therefore, although it's got very, very important properties that can be used in any biological related properties there, or biological fields thereof. So as you increase the amount of chitosan, you end up with more lesser fibers and starting to form some beads. And you don't want beads if you are really trying to make fibers. The challenge there when you're making fibers to be able to eliminate as much beads as possible. And the same thing happens when you look at now chitosan PVA blend by varying the voltage, that you can be able to see that as you increase the voltage up until about 19, they reach a critical point where, because of high electron density charge in the material here, you end up with lowering of your fiber diameter. And now if you look at this scenario here where you looked at a cellular acetate and your polyacrylonitrile and loading that is TiO2, such that first the same observation that's been made before, where if you increase the amount of the polymers themselves, you end up with an increase in the diameter. But this TiO, what it looks like, and being embedded inside the polymers, you end up with different features altogether. But here you can see that indeed, as you increase the amount of the diameter is increasing as you increase the amount of concentration, and the same thing happens here as you increase the voltage, especially because the highest voltage where you've got higher electron density, the diameters becomes even smaller. So this has also been tested once you've loaded the nanoparticles into the fibers. Same observation here about the average diameter also increasing with the addition of your nanoparticles. And you find that actually E. coli shows the most activity against these nanoparticles or the nanofibers embedded with nanoparticles as compared to perhaps your Staphylococcus aureus. So one of the things that we also currently are doing, and this is work that we're also doing with the collaborations from University of Masai Mara in Kenya, was also to try and see, since there's a lot of problems with malaria in the region, was also to try and see if we can be able to embed some not nanomaterials by this time, but some mosquito repellent materials into the polymer fiber such that we can explore their slow release into the environment. And the slow release means that once they're embedded into the polymer fibers, and you can be able to monitor how slowly they release the active compounds like eucalyptus in this case here, then you can be able to incorporate them into things like your cloth headband, your cloth leg wrist, and your cloth leg band, and also your wristband. And therefore, it means you can comfortably sleep with your your wristband or your leg band or a headband, depending on which one you feel comfortable with, and still be able to repel mosquitoes from the environment, or maybe to be embedded inside the environment where you're sleeping so that those can repel mosquitoes in a way. And this is some of the work that is still underway. And also, we're also exploring, for instance, mixing the copper and silver nanoparticles because they've got very strong antibacterial activity, whereas copper also have got strong antibacterial activity, but also it's very cheap to, if you mix it together with silver, and because they can be able to deal with both, gram-positive and gram-negative bacteria, and in any environment where you've got chronic wound, you've got so much variation of bacteria in there that makes the wound to be infested and not to be able to heal. And we're hoping that perhaps by mixing these two and bury them into the fibers, we can be able to deal with things like chronic wounds. This is still also work that is still underway at VUT. And the other one is that of trying to embed also some active compounds from plant extracts that are known. There are some plants that are known to be very much active against things like the bean weevil, and such that if you incorporate those plant extracts into the polymer fibers, together with the silver nanoparticles, we are able to explore as to whether they can be able to repel the bean weevil, such that you know that the bag itself where the seeds are carried, it can be covered by, or it can contain these polymer fibers such that they can be able to repel, the bean weevil. And that can be able to help a lot in agriculture, because you can imagine having spent a lot of time plowing, and then at the end of the year, when you're supposed to be reaping the rewards, the bean weevil, they infest your material, and then you end up losing a lot from that. But also the silver nanoparticles, they are very much useful in the sense that they could assist us in be able to deal with things like your mold forming there. So if you incorporate silver into there, you also can be able to make the bag to be long-lasting compared to when there's no silver nanoparticles to be able to prevent the mold. And the plant extracts also have been explored in their cooperation to the polymer fibers, and some of those polymers like cellular acetate and your polyvinyl pyrrolidone. And we also try to see, once they, since we know that plant extracts have got some antibacterial activity, if they are incorporated into the polymer fibers, especially this blend that we've used here, they seem to be giving rise to very good response to the E. coli and Staphylococcus aureus as well. So these are some of the work that is still also being going on at VUT currently. And some of the students, I think, should be able to graduate from some of this work and also be able to give us some bit more conclusive evidence to what really will transpire from those activities that you're exploring there. And now, just for the sake of those who are still doing, who are starting up with their research and younger researchers, and not that I will claim that I'm very old, because I still have probably another 20 years before I retire. Just to as an advice, I think if you look at the way our materials, we've got a lot of technologies that have been developed, products that have been developed, and a lot of them, they become part of the waste and they become part of the environmental problems. And therefore, the best things for us as researchers in going forward, which is, I think, is going to be the next big challenge, is to be able to get our products that we are developing as new products that can be able to solve the current problems and find use for them in other ways. So we're finding alternative use to the same new materials or devices that we are making will probably be the best new challenge that, as researchers we can be able to focus on. And therefore, my advice will be that the future is finding new uses for recycled or newly developed materials or technologies. So besides doing all this research, we've also been spending some time celebrating, once in a while, celebrating with research groups. And this is a group of students from both VETs, which is my biggest collaborator, and the VUT in 2017. And this is what was happening when we had a bit of a braai and a couple of faces that I've highlighted there. These are some of the collaborators that are key in getting that group together. I would like to lastly perhaps acknowledge first University of Zululand, where I started together with Manchester, and alongside them it was NRF, together with Royal Society, where they gave funding to make it possible for one to visit Manchester and spend some time there to complete my PhD. And University of Witwatersrand, some of the work has been done from there. University of Johannesburg as well. I spent, I think, about 2 years in both universities, or less than 2 years, where at least we have done some work that I've also shared with, and some students that graduated from those work. And also, electron microscope unit from UCT, which I think has been supporting us a lot. And so we've always been sending our samples to be analyzed for SEM and TEM from them, over the years. And lastly, Valley University of Technology, which is a place where I think I've done most of the work, almost like 10 years of the work that I've presented here, mostly is come from VUT. And just finally to just say, in the journey of trying, I think you probably will remember at some earlier stages where NRF and also Department of Science and Innovation effort was to try and say, can we as researchers also work on human capital development? And I think one have done a good job on that, such that you can see a list of students that have graduated, and a good number of them went on to do their PhD beyond the master. Some of them with me, some of them elsewhere. And some of them are also based at INANOS here, which I think the following year they should be graduating to also become doctors, and some of them at VT as well. And just maybe a special thank you for the postdoc, Dr. Mbali Sibia Matlambi, who was the first postdoc that I had, and she actually knew nothing about nanotechnology before joining the group, but I had a drive to say we need a South African female postdoc at the VUT at that time, funded by VUT, to say if she can be able to help me to drive the quest for doing all these starch-related, sucrose and sugars-related studies on silver-based nanomaterials there. I think, and she really did well as a postdoc in that area. And lastly, I just want to acknowledge people who really also have played a key role, starting with, for instance, Professor Dakwa from our masters. I think he's really played a very important role from my honors to masters. And I was encouraged when I finished my honors to say there's no way that if I can be funded through grant holders, I should be able to pull back and not finish my PhD. And here I am today, at least getting integration from Professor. Thank you, Professor Doga, for that, and also for constant support messages. And University of Zululand, together with Professor Brian from University of Manchester, he's late now, but he's played a very important role in getting me really where I am in terms of learning about nanotechnology. That's where we really started learning about nanotechnology. And I think some of the things that people don't know is that when you do research, and perhaps you're young, some of the established researchers, they don't normally easily open doors. But I think for me, people who were able to open doors and start working with me are younger people. So Professor or Dr. Lucky Scooby-Doo, who was at the CSR, helped a lot with the course busing of students and opened the doors for using some of the equipment at the CSR. And now is at MITEC. Dr. Philemon Matabula, who was not a doctor at that time, was still just a student. We started working together alongside with Dr. De Vries, who was working with him, was reporting to him. And I think we learned a lot from electrospinning from these two guys. And also, just to thank people at VUT as well, there's Dr. Mkumbeni, there's Dr. Feljun, even though I know she's retired, but thanks very much for hand also working alongside with me. And Dr. Takaiza as well, who's helped a lot with these two. I think they helped a lot with some of those antibacterial activity that we have been exploring there. And I'm glad that they really opened the doors for us to try and start exploring what these nanoparticles can do. And finally, or just one last before the list of the people to perhaps acknowledge is collaboration at University of Masai Mara, and this is Dr. Wesley, who's been the instrumental person to get us to where we are on that collaboration, and did some work with them there. And finally, yes, my wife, who have also been, she's been my strongest collaborator. I think we've worked very well together with different students being co-supervised and also different aspects of the work thereof. And I just want to say at the end that just to note that research is a challenge and it requires a lot of hard work and also work smarter, and also have to have a lot of integrity, honesty, and navigating, around, a way around those challenges is very important. Just for those who are still, coming up in research, for you to take note of that. And I would like to, at the end of it all, thank you all for listening, and thank you all for the invitation and everyone else around here. Thank you very much.
The Principal, Research, Postgraduate Studies, Innovation and Commercialization, Professor Meiwa, Executive Dean, the College of Science, Engineering and Technology, Professor Mamba, the guest speaker, Professor Moloto, his family, staff, and students. A very good evening. It is my pleasure to respond to the inaugural lecture titled The Realities of Fabricating Nanomaterials, Past, Present, and Future Prospects by Professor Justice Moloto from the Institute of Nanotechnology and Water Sustainability in UNISA. Let me be the first to congratulate Professor Moloto on his induction into the professoriate. Hearty congratulations and welcome to the club. Nanoscience and nanotechnology has the potential to develop solutions to many challenges facing society today. There is exponential growth of applications of materials at the nanoscale within emerging and established technologies. New materials would improve properties, dominate applications within the field of energy, water treatment, and medicine. Professor Moloto was one of the first formally trained researchers in the exciting area of nanotechnology. He initially gained valuable knowledge in inorganic coordination chemistry while doing his master's at University of Western Cape. He moved to UniZulu in the early 2000s, where he enrolled for a PhD while taking up a position as a lecturer. This transformed his career, giving him an opportunity to get international research experience, working with the late Professor O'Brien in Manchester. The work he has presented in his lecture today shows his vast knowledge and expertise within the field of nanoscience. He presented work on the synthesis of metal nanoparticles and their interactions with nanofibers for applications in the biomedical field and water treatment. The processing of nanomaterials within the matrix, such as the polymer, is a contemporary area of research. Professor Moloto has made great strides within this niche area. He outlined his initial work on the synthesis of nanomaterials using single source precursors, which was then extended to the applications for water treatment. Some of the shortcomings of the single source route were outlined. He then described how these could be overcome by the ligand exchange mechanism, whereby the inorganic capping groups can be exchanged for water-soluble ligands, potential biomedical application. He also described the preparation of silver-based nanomaterials using plant extract. This green approach to nanomaterial synthesis is very topical. He also gave examples of metal chalcogenide nanomaterials which could be prepared using amino acids as capping groups. These bioconjugates were then tested for antibacterial properties. Finally, he has presented findings on the preparation of the polymer nanofibers using the electrospinning technique. The embedding of nanomaterials within these polymer blends opens up a wide array of applications, harnessing the properties of both the nanomaterials and the nanofibers. Professor Moloto will continue to be one of the key researchers pushing forward the boundaries of nanoscience in South Africa. I once again congratulate him on his well-earned position as professor at UNISA. May he go on to greater heights in his career. Thank you.
Wow. You will agree with me, ladies and gentlemen, colleagues, that we really have been eating from a well of expertise. Thanks, Prof. Moloto, for a lecture that was so educational, an acknowledgement of the extent of your scholarship and its societal significance. We thank you for that, and we thank Prof. Moloto's family for attending this lecture, for gracing it. We thank everybody who has graced this lecture and sought to attend it going into the evening. We also singularly want to appreciate Prof. Reva Brazadu for a very engaging response that is leading. I express immense gratitude, ladies and gentlemen, for your support, not only, of course, of this lecture, but of Prof. Moloto's scholarship. Gratitude goes to colleagues who have not come to the podium, like all the colleagues that have been to the podium, who've worked behind the scenes to ensure that the technical aspects of this lecture, the logistics of the lecture, and everything related to it that's not presented on the stage is successful. And these are colleagues from DIA, from media, from video technology, from IT, from the facilities, and all the colleagues who've made it possible for this lecture to be this successful. Thank you to every one of you. Good evening.